Welcome back. We are still on the TD3 problem set. And now we're going to look at the Barrow-Gordon model. So whereas the Samuelson multiplier accelerator model extends our macroeconomic toolkit to include intertemporal dynamics, the Barrow-Gordon model is going to be our first crack at including optimization and microfoundations. And in particular, we're going to study one sense of how the Lucas critique operates. So we discussed in the TD, in the previous videos, that the Lucas critique is this idea that if you naively try to apply a model or apply a policy that doesn't think about the feedback loops, the consequences of that policy, the policy will be thwarted in the wrong one, in the long run. And this is exactly what we're going to see in the Barrow-Gordon model. That when the central bank tries to naively apply a policy without thinking about the people's reactions to that policy, they will fail in their objective and they'll make everybody worse off. So let's begin. We have an economic growth function, an output function. So this is y equals c plus I plus g in disguise. And now we're simplifying it down a lot because we don't care about studying consumption or investment or government expenditure in this model. We only care about this dynamic interplay between households and the central bank. There's a nice lesson here. When you think about writing a model, make it as simple as possible. Make it as parsimonious as possible. Cut out all the bits that don't apply to your research question. So our research question is just this interplay. We cut out CIG. We leave just this inflation, this real inflation. And that's all. And then we're going to have two actors. They're going to play a game. The central bank will follow a Taylor rule to help them to choose targets for y and pi. And then the household will also have a utility function where they will feel bad. So there's a minus sign here. They will feel bad if they guess wrong about what the central bank's inflation policy will be. So the central bank is going to have a target in mind. It's going to choose a y, it's going to choose a pi. And then, simultaneously, the household is going to guess what will that policy be. And then we'll put all the solutions together and see what happens to the actual inflation to output into welfare. And that's going to be our research strategy here. So part A asks us to provide an economic interpretation for the following parameters: yn, a, epsilon, and lambda. Okay, so we said that yn, so note 1, we noted that y is total economic output. I guess it's growth, so we're normalizing. And we see it's linear. 2, we see this is a linear function. So when we have a linear function, there's only two roles that are played by anything. There's the slopes and there's the intercept. So, for linear functions, there are slopes, which are marginal effects, or if you like, they are sensitivities, or if you like, well, I was going to say they maybe are elasticities, but you have to be very careful with that interpretation, okay? So let's just leave it here. They are marginal effects, they're sensitivities. And these are words you should use when I ask you, what does this mean? You need to say something like this. For intercepts, we talk about baselines. We talk about natural rates. like the natural rate of inflation or the natural rate of unemployment. This is what it would be if there was nothing else, right? If the inflation gap here, this expectation gap, if I suppose it's the real inflation rate, were zero, then we would just be left with yn. So it's like the natural rate of growth. It's how much the economy grows absent this effect that we're thinking about. Okay. So yn is not a slope. It is an intercept. So we can say therefore that yn is the natural rate of growth, or the baseline rate of growth. Wonderful. How about a? Well, a appears next to a variable, so a is a slope. We see that a is a slope in a linear equation. Therefore, a is the marginal effect of real interest or real inflation on growth. Okay. Yeah. Maybe real inflation is not a good word. I've been saying this real inflation. I think that's incorrect, and I apologize. We can think of it as surprise inflation. How about that? Surprise inflation. Why? Because there's some amount of inflation, and then we subtract off how much we thought there was going to be. So if these are equal, then there's no surprise. If the expectation is too small, and it's a positive or negative surprise. Okay, so it's the marginal effect of surprise inflation on growth. Great. Next we have epsilon. What is epsilon? We have this statement here, and so we need to know how to read this. The funny squiggle means is drawn from, or follows up. Okay, so epsilon is drawn from a normal distribution with mean 0 and standard deviation sigma epsilon, or epsilon follows a normal distribution with mean 0 and standard deviation sigma epsilon. Epsilon is a random variable. It's an exogenous shock. You need to know that in macro, these random effects are always going to be exogenous shocks, things that are outside of the model that just come and we just take them as they are. It's news, it's the weather, it's war in other countries, it's political upheavals, it's scandals, it's anything. The invention of a new technology, everything else that is not surprise inflation is in epsilon. Okay, and then we also have, what else? We have lambda. Now lambda appears here. This is kind of like a linear function if we think of pi squared as being one term, right? But more importantly, you should recognize that this is a Taylor rule. This is a Taylor rule. And you see it's a utility. So parameters here in utility function are going to be controlling how much agents care about or like something. Right? If lambda is 0, the agent does not care about y. If lambda is 1, then the agent likes y. He or she receives 1 unit of utility for a 1 unit increase in y. If lambda is negative, then he dislikes y. So lambda controls the degree of feeling towards y. So you can write that lambda is like a sensitivity parameter. Yes, it's like a sensitivity parameter. Or like a decision parameter. Not really a decision parameter. How much you like it. It's a sensitivity. Okay. sensitive, sensitivity. And in this case, it's sensitivity of the central bank to changes in economic growth. Great. Okay. So with that in mind, with this definition of lambda in mind, we can move to the next question. So keeping this in your head, we can move to question B, which asks, what is the level of economic growth that would maximize the bank's utility function? Well, the utility function is with respect to growth. So let's ignore this because we're just talking about growth. With respect to growth, this is strictly increasing, right? What's the graph? The graph is a straight line with the slope is lambda, right? So what is the maximum of a straight line? It's plus infinity. It's plus infinity. So the first part of your answer, part 1, is plus infinity, given lambda greater than 0, which makes sense. It doesn't make sense for the central bank to hate growth, right? So we say lambda is greater than 0, and therefore the optimum amount of growth for the bank is infinity. Would the bank ever lean into the wind to cool off the economy? Well, we recall that leaning into the wind is when the banks raise interest rates when the economy is going too hot, when asset prices are too high, when everybody's getting too excited, to calm everybody down, to stop growth. So would this bank ever stop growth? No, because it wants infinity growth. The more growth, the better. So no, it would never stop. It would never lean into the wind because it would never stop growth. It always wants more and more and more and more. Okay, perfect. And let's do C very quickly because C is not so complicated. It's just going to make a point about the 1/2 on the utility function for the bank. Okay, so we have the bank's utility function. I'll write it again because it's not so easy to erase in this program because I wasn't smart enough to set up like layers and stuff. So the utility for the central bank is lambda y minus 1/2 pi squared. And so we know what is lambda. We talked about lambda being a sensitivity parameter, right? We talked about lambda as sensitivity. sensitivity. But what about here? We don't have a sensitivity parameter for pi, and why not? Instead we have this 1/2. And what is this 1/2? Okay, so it says to plot, okay, sorry, I went over here, but also we have one here, right? So, I mean, the point still stands. We have no sensitivity parameter to being wrong in the household utility function. Instead, we have this 1/2. So what's going on? Let's do it. So it says plot the household utility function at pi equals 0. Okay, I'll do that. Here's my x-axis, and here's my y. Come on. Here's my y-axis, and this will be 0. And so let's do some test points. So when, this is going to be the expected inflation, and this is going to be UHH. So UHH equals minus 1/2 expected inflation minus inflation squared. So when expected inflation is 0 and this is 0, we get 0 minus 0 is 0, 0. Okay, so our first point is 0. Now let's test 1 plus 1. When 1, we get expected inflation is 1 minus 0 is 1 squared is 1 times 1/2. We get minus 1/2. Okay, great. Let's come down here. So here we have minus 1/2. And by symmetry, because we have a square function, right? The square function means that the minus and the plus will have the same value. So we get also here as well at minus 1. It's minus 1, this is 1. We also get this, okay? And of course, we realize this is going to be a parabola, a downward facing parabola that touches 0, right? And we can see that it touches 0 by noting that at 0 it equals 0. So that's a critical point, right? Okay, great. Check. This is our utility function. What is the maximum value? The maximum value is 0, right? So max UHH equals 0. Let's get some points. What is the minimum value? Well, it goes down forever. So min UHH is minus infinity. It's unbounded. Okay, on the same graph, plot 2 times UHH. So what this is saying is it says now we're going to consider a different function. We're going to consider 2UHH, which equals just minus e pi minus pi. Okay? So we're going to get rid of this minus 1/2 and instead ask what happens. So again, let's just do some points. At 0, we still have 0, right? So we're still here. And then at 1, we get 1 minus 0 squared is 1. So at 1, we get, yeah, so we're a little farther down, right? Because this is 1/2. I got confused because I thought that was 1. This is 1 here. Okay, so at 1, we're down here now. Okay, once again, we say it's a parabola, but it's kind of tighter than this other one, so it's always going to be inside. I think so. Do they cross at some point? I don't know. At any rate, for the little bit that I drew, they're both. This is inside of here. So, for 2UHH, we see that the max of 2UHH occurs where it turns, and it's exactly identical to max UHH, which is 0. Okay? This is an important point. It says, comment on the effect of putting minus 1/2 in front of the quadratic utility in terms of, 1, the optimum value of the utility function. Well, the optimum value is the same. The optimum value of 2UHH and UHH is the same. What this means is that if we maximize this function, okay, if we maximize 2UHH, it's exactly the same as if we maximize 1/2 UHH. Okay, so we can choose. If all we care about is maximum value, right, which is all we care about, we're going to solve, we're going to make a Lagrangian. We're going to solve an optimization problem. We only care about this maximum point. We're going to do all of our work here. So we only care about this maximum point. If we're going to do an optimization and we only care about that point, then we have the freedom to multiply by whatever we like. Doesn't matter. So, part 2, why should we multiply by this? It says, make a comment in terms of ease of calculation. Well, we're going to take a derivative. And when we take a derivative, we will take the chain rule. When we optimize UHH, we will get, as part of the chain rule, we will get this 2 coming down. We will get minus 1/2 times 2 times e pi minus pi, right? That's the outside of the chain rule. We brought the power rule down. So if, or by having the 1/2, we cancel the 2 and avoid an unimportant constant in all of our equations. Okay? So the argument goes, 1, it does not matter for the optimum point. Okay, if we cared about a point down here, it would matter. But we don't care about points down there. We only care about the optimum. At the optimum value, 2UHH and UHH are the same. So we are free to put 2 or not put 2, put minus 1/2 or not, right? It doesn't matter. And by putting 1/2, we have the effect of making this 2 from the chain rule go away. And then we don't have to worry about later down the road when we're doing some messy computation. There's a bunch of 2's floating in our equation. It just goes away. So that's nice. It helps us out. Okay, so this is why when we have a quadratic utility function, you put you put these normalizing coefficients in front. Okay, so I really wanted to motivate the presence of those. We'll see it, you see it even with other coefficients, right? When we look at RBC, you'll notice that sometimes we'll write down something like U, and then that'll equal like C, 1 plus sigma, divided by 1 plus sigma. Why do we divide by 1 plus sigma? Because when you take the derivative, this will come down, these will cancel, and it's exactly the same. It's the same exact argument that you have up here. Okay? This was long, but that's what times 2 and skipping around is for. Thank you for watching, and I'll see you in the next one.